Hello, and today we're going to be talking about something called percent composition, which is a pretty interesting analysis tool, I guess is the best way to say, and also to identify in regards to experimentation of how much of what you're working with. Again, if you don't have a calculator or notebook paper to take notes on, I will go ahead and get that out. That way you can follow me along, pause the video, do those examples that we're going to be doing on your own, and then we can double check. But after this, if you have any other questions mathematically or conceptually wise, please come talk to me, and that way we can make sure you have this ingrained and ready to go for tests and quizzes. But what is percent composition? So the percent composition is the percent of mass of either an element or a compound within a particular sample that you have. So the whole point is to say if you have a sample of multiple compounds and stuff, if you need to determine how much of a compound is within that sample, you can do that mathematically. And so to calculate percent composition, you have to find the molar mass of the sample, okay, and then you have to divide the mass of the element or compound by the molar mass of that sample. So, and then you multiply by 100% to get that percent unit. So the way you can do it is that percent composition, if I get my mouse here, percent composition is equivalent to 100%, okay, times the molar mass of whatever element or compound you're trying to identify the percent composition of, divided by the molar mass of the entire sample that you have. So if you have carbon dioxide, oxygen, hydrogen, or whatever in a huge gas sample, that would be the entire molar mass sample size. And then you, if you were trying to find just the molar, the percent composition of oxygen, you would take molar mass of oxygen divided by that mixture there. Another way I always talk about it too is that it's kind of a condensed way if it works better for you is the percent composition is 100% times the part that you're trying to figure out divided by the whole that you're given. Okay, so the whole sample and the part is that percent part that you're trying to figure out mathematically. So just to kind of do a little practice, kind of dive right into this. What is percent composition of hydrogen in a molecule of water? Well, we know that H2O is the molecular formula for water. So for every 2 hydrogens that I have, I know that the gram atomic weight or the molar mass of that hydrogen is 1.01 grams per mole. Therefore, I have 2.02 grams per mole of hydrogen within water. And then I have oxygen atom too, which is 1 times 16 grams per mole, and so therefore I have 16 grams per mole, which means my total sample, which is water, is 18.02 grams per mole. Now I didn't say how many moles of it. It says percent composition of hydrogen in a molecule of water. So 1 molecule is 18.02 grams per mole of that. Okay. So what this says is it equals composition of hydrogen is equivalent to 100% times the part of hydrogen that we're trying to figure out, 18.02 grams per mole that we're trying to figure out. That's the water, so that's the whole sample that we have. So hydrogen makes up 11.21% of water. Okay, so majority of the mass is from the oxygen, but hydrogen makes up 11.21%. Okay, so again, the part that we figured out of the whole that we figured out of that molecule. Now you're probably wondering, well, this is per mole. Well, they cancel out. The thing is, if I have 1 mole of water, it's still going to be 11.21% hydrogen because they're directly proportional to each other. As I increase that sample size, as long as the sample is the exact same stuff, that percent composition is going to be the exact same no matter how big the sample is. Okay, so again, this goes based off of units. Those units cancel out the way we want to, and I'm left with percentages, and it works exactly like those mole conversion problems. So just look for the units that you're looking for. So again, those cancel out. So this one's a little bit more interesting. So what is the percent composition of a compound that contains 12 grams of carbon, 48 grams of hydrogen, and 32 grams of oxygen? Well, we have to figure out the total mass of the sample first. So we know it's made up of 3 different things. So we know the total mass is the addition of all those masses of the elements together. So 12 plus 48 plus 32, you get 92 grams for the sample mass. Okay. Now, I'm just trying to figure out the percent composition. So the thing is, these masses are going to cancel out. So I just want to figure out carbon. So I put the 12 grams of carbon, the part of the total mass I'm trying to figure out, and I divide it by the total mass of the sample that I calculated before, times 100%, and it turns out carbon makes up 13.04% of that. But I can also determine the percent composition of hydrogen. Same thing, it's just now I'm putting 48 instead of the 12 grams of carbon. Now, there's 3 parts. There's carbon and hydrogen. We've already solved carbon and hydrogen, and we know that 100% of the sample is made up of carbon, hydrogen, oxygen. Well, if we know the 2% of the other 2 parts, you actually don't have to do all this calculation for the 3rd part. What you can say is that we know 100% of the sample is accounted for, and we know the percent of each element. So what we can do is that percent of oxygen we can say is 100% minus the addition of the percent compositions of hydrogen and carbon. And then we're left with it being 34.79% oxygen. So if I add these all up, it should equal 100%, which is that total sample. Okay. All right, so in this one, if you were given a sample of 1,041 grams of sodium chloride, what would be the mass of chlorine with the sample if chlorine has a percent composition of 60.65? Okay, so what I have to ask myself is that the mass of chlorine is equivalent to the total mass of the sample, okay, times the percent composition of chlorine divided by 100%. So what I did is that now I'm trying to find the mass of the chlorine. That previous equation was solving for the percent composition, so I rearranged the equation mathematically to solve for the mass that was on top of the division line. Okay, so to kind of go back real quick, I'm now solving for this instead of percent composition. The percent composition is already given to me in the problem. So you might encounter problems that where you're already given the percent composition and you need to solve the mass of that. So I'm trying to find the mass of chlorine itself. So I plug it in, I have my total mass of my sample times the percent composition divided by 100, which is pretty much just going to be a fraction. So it's 1041 grams times 0.6065. The percents cancel out, so there's no percentage here. I'm just putting chlorine, okay? And so what I do is I'll end up with grams of chlorine. So I have 631.37 grams of chlorine out of that 1041, okay? So we know that out of the 1041, if it's 60.65% chlorine, then that means that it has to be 631.37 grams of chlorine out of that total 1041. And if you wanted to figure out the amount of sodium, then you can just take 1041 minus this, and that would be your mass of sodium. All right, hydrated compounds. These are interesting compounds and very, very important to understand because dealing with all the chemicals that we're going to have in class, a majority of them are going to be hydrated compounds. So you need to know how to properly look at the bottle, know what you're working with, and kind of go from there, okay? So hydrated compounds is that during crystallization within an aqueous or water-based solution, ionic compounds become surrounded and absorb water molecules within the lattices. So ionic compounds, they kind of bond in layers. In water, since they're polar, they want to be attracted to the charge difference between cations and anions. So they get kind of surrounding the compound, and they slightly bond to it, and also they can get sucked into the compound itself. So due to that, the mass of the compound changes. So this is what we call hydrated compounds. So when it comes to this, hydrated compounds are represented in chemical formulas in a particular way. So if I had sodium iodide, okay, sodium iodide that's hydrated, what I would say is that sodium iodide, for every 1 mole of sodium iodide that I have 10 moles of water attached to it in some way, okay? The dot does not mean multiplication. Okay, it does not mean multiplication. It just means that there's 10 moles of water attached to every 1 mole of sodium iodide. The names of hydrated compounds include a prefix. So the same prefixes as covalent compounds. They're just followed by the word hydrate. So if I was to name this, I would say sodium iodide deca for 10 hydrate. So the mass of water has to be accounted for too when we're performing percent composition calculations. I'm going to go over here in just a second of how that works. So determine the percent composition of water molecules within sulfuric acid pentahydrate. Okay, so sulfuric acid is H2SO4. Pentahydrate means there's 5 waters. For every 1 molecule, there are 5 waters around it, or for every 1 mole of sulfuric acid, there's 5 moles of water surrounding it or absorbed in it. Okay. So what I have to do is I have to calculate the entire mass of this, which includes the mass of the water. So my hydrogen's 12, that comes from the 2 here, and then 5 times 2 here. So that's where I get 12 from. Oxygens, I get the 4 here, 5 times 1, so 5 plus 4 is 9. And then the sulfur is the only one that I have here. So I calculate the molar masses of each one, add them up. So the entire molar mass of this entire compound, this one single compound, is 188.19 grams per mole. Well, I'm wanting to define the percent composition of just the water molecules. So what I do is that I calculate the molar mass of just the water molecules by itself. I say 5 moles of H2O is equivalent to 5 times 18.02 grams per mole. Okay, and this 18.02 just comes from adding the 2 hydrogens and the 1 oxygen together. Okay, and I get 90.1. So then I do the percent composition of H2O is 100 times the part, which I'm trying to figure out, which is the 5H2O. Okay, and then the mass of the entire compound itself. So I do percent comp of H2O is 100 times the 90.1 grams per mole that I solved down here, divided by the entire mass sample, or the molar mass of the entire sample, which is the 188.19 I solved here. So the percent composition is 47.88% water. So out of this entire compound, water makes up practically half of the mass of that. So, you know, water can have a very big deal depending on how many waters are attached to a particular compound. We'll do another one. So determine the percent composition of just hydrogen within phosphoric acid octahydrate. Okay, so phosphoric acid looks like H3PO4, which is also the same thing as hydrogen phosphate. Okay, so this here, okay, is 8H2O because octa means 8, hydrate means water. Okay, now it's asking for the composition of just hydrogen, so I'm still going to break it down like normal. My 19 hydrogens comes from the 3 here, and then the 8 times 2 here, so 16 plus 3 is 19. 12 oxygens comes from the 4 here, 8 times 1 is 8, 8 plus 4 is 12, and then I have the 1 phosphorus. So I add them all up together, and I get my entire compound molar mass is 242.16 grams per mole. Now, I know that I want just the composition of hydrogen, so what I do is I take the part that I know about, that I calculated, okay, I'm going to plug it in for the mass of hydrogen of that entire compound, and I'm going to divide it by the entire compound molar mass itself. So I'm 19.19 grams per mole divided by 242.16 grams per mole times 100%, and the percent composition of hydrogen within this entire compound is 7.92% hydrogen. Okay. All right, so I know that was kind of fairly quick, but I want to kind of show you a couple of examples of how these problems can go. If for any reason you have any trouble with the math or still have additional questions, please come talk to me, email me, talk to some of your classmates if you need to for further clarification as well if I'm not available for some reason. But we're starting to get deeper into the math of this, so if there's things that I'm doing in these videos that you don't understand, please come talk to me and I can break it down more step by step for you. I really want to help you with this. I don't want to make this class harder than it probably already is for you. So thanks for watching this video, and hope to see you in the next one, and see you in class. Bye.